Okay, so 3.5. Now we want to see the derivatives of some trigonometric functions. That means sine x, cosine x, tangent of x, cotangent of x, secant of x, and cosecant of x. Okay, and these are actually related to each other. You will soon see that uh, that the derivatives of sine x is cosine x, and the derivative of cosine x is negative sine x. You'll soon see this. So these are actually related. Um, I mean, the derivative of one trigonometric function is actually is definitely one of the other, one of those six uh, trigonometric functions with the plus minus signs anyway, or at least the product of those. Again, we'll go to that. But first, let us see the theorem. It says, whenever limit x tends to 0, sine x over x will give us 1. Okay, and cosine x minus 1 over x will give us 0. Okay, let's see why. So first of all, let's take some random values from either side when we are approaching 0. And if we are approaching 0 for this particular function, sine x over x, from either side, are you trying to say? Can you please unmute yourself? Tulope, I'm muting you. If you need to unmute yourself, just let me know.
Yeah, what are you saying, sir?
Okay. So if we approach from the left, that means, sorry. That means from this side, if we approach from the left side towards 0, the sine x over x will have this value, 0.9983. You can actually check this using your calculator. Same thing will happen if we approach from the right. So no worries with that. But we want to see if we go really close to 0, then where does it take us? We are still doing the concept of some basic concept of limit. If you remember, for finding limits, we actually approached from either side and see whether it takes us to the exact same point, right? And if we go really close to 0, we can actually increase the number of zeros here, a couple of more. If you add a couple of more zeros, you'll see there will be more nines here, 0.99999, and it will keep go like this. So this means, as you can see, this value is increasing, right? Where does it, or rather I'll say, where will it take if it keeps going like this? What do you think? As you can see, it's going really close to 1. Do you agree? It's 0.998, then it's 0.999, and you can see the number of nines are getting increased here. So your assumption might say, hey, it looks like it's going really close to 1. Do you agree? Again, it's the algebraic approach which we don't need to use anyway. It's just the calculation you do to verify, but you don't need to do it for any homework or any exam. It's just to make you understand how actually you can do this algebraically if you somehow need it. Okay. Now, if we see the graph again, if you graph it using the graphing calculator or any other graphing tool, you'll see doesn't matter which side you are approaching from, even though there is no defined value for zero, for this function. If you approach from left or if you approach from right, this function will take you to this one. And again, at zero, we don't need a defined value for the limit to exist. We know that, right? That's actually one of the requirements for continuity, not for limit. So even though there is no defined value for x equals 0, because we know that at x equals 0, the denominator, at least the denominator is 0. Even though on this occasion the numerator is also 0, but that's not one of our concerns. Since the denominator becomes 0, that means we don't have a defined value at 0, right? But still, it's taking us to the same point if we approach from either side, right? So that's why we say whenever x tends to 0, I mean x approaches to 0, the limit for this function will take us to 1. And we'll be using this theorem for some trigonometric functions in future, for finding or for solving problems with a format like this. We'll be getting some problems where we'll be using this theorem to solve our problem. Okay, this is one of the theorems, one of the 3 theorems, I guess. We'll have 2 more. If we don't have on this graph, I'll let you know. Uh, um, I guess, yeah, I guess before we finish today, I'll definitely let you know. But I'll wait for it. I guess they will have the next 2 as well. If they don't have, I'll write it for you. Okay, but we'll be using those 3 theorems to solve some problems. Okay, any question from this? It's still the concept of limit. Okay, but still, if you have any question, you can unmute yourself. No question at all? Okay. Now, let's see what we have next. Okay. So let's take a look at this graph. So as I said, if you remember, I actually revealed the secret a couple of minutes back. What is the derivative of sine x and cosine x, right? So as you can eyeball the graph, you can see it's saying that the derivative of sine x is actually cosine x. Now you might be wondering, why is that, right? You might be thinking, why is that happening? I mean, if I find the derivative of a sine function, why it's giving me the cosine function in return, right? Okay, so if you're trying to find the derivative, that means if you are trying to find the instantaneous change of rate for the function at any point, what happens? So let's say you are trying to find the derivative here at, I guess it's pi over 2, yeah. Yeah, it's pi over 2. At pi over 2, if you draw a derivative, or rather I would say a tangent line, you will see it's actually parallel to the x-axis. It's a horizontal tangent line, okay? And same goes for 3 pi over 2, 5 pi over 2, so on and so forth. So whenever you are trying to find the derivative of sine x at these points, you will see it's just the horizontal tangent line, or I'd say it's just parallel to the x-axis, like this, the reddish one. Can you see that? Okay, now what does it give us? So if you find the zeros of cosine x, I mean, if you solve the function cosine x, if you set it to 0 and find it, or rather solve it for x, you'll see these points are nothing but the zeros of cosine x. That means if you solve, if you set cosine x to 0 and solve it for x, you will see the values of x are actually these points. This, what I mean by this point, I mean these values of x, pi over 2, 3 pi over 2, like this. Okay, these are actually the zeros of cosine x. So if you draw a graph of cosine x, obviously uh, you'll get a graph like this. This is the graph of cosine x, and you will see even if you don't find the zeros of cosine x, you can still eyeball that cosine x crosses the x-axis at these points. You can see this is the pi over 2, this is 3 pi over 2, and it keeps going like this. Wherever it crosses the x-axis, you can see at those points, what happens? At those points, the y values for cosine x is 0, right? Because if you remember the basic algebraic approach or basic algebraic methods, at x-axis, on the x-axis, I would say, the y value is always 0, isn't it? Right? So the graphical representation of these functions uh, is, is actually giving me an idea that the tangent would actually, I mean, the derivative of this function would actually be related to this, right? Because I'm drawing a tangent line here, and it's actually the zeros of the other function. And this tangent line is creating, and you might be wondering why, right? I'm actually slowly going there. So this tangent line is actually horizontal or parallel to x-axis. And if you remember, we said whenever a tangent line is parallel to the x-axis, it's either creating a 0-degree angle or a 180-degree angle, right? Whenever it's parallel to the, whenever two lines are parallel, the angle between those is either 0 or 180, right? So on this line, on this particular line, your angle with this particular line is 0. Do you agree? Because it's actually, if you consider this x-axis, it's creating a 0-degree angle with the x-axis. Do you agree? If you just draw another line, an imaginary line on this x-axis, a line on itself is creating a 0-degree angle. Do you agree?
Yes, because it's matching up with the, I guess you could call it the parent line if there's no deviation, or well, if there's no movement up or down, there's no angle.
Right. Or if I go this side, if I draw a line this side, this will create 180-degree angle with this line. Do you agree? So this should tell us graphically, although this is not required for us, but I want you guys to know why this is happening. Okay. Again, you will not be asked to do anything like this in the exam, at least. That's for sure. You'll be only asked to find the algebraic problems. But the graphical idea, uh, you can actually uh, see that why it's happening, right? And now let's see what's happening for the cosine x. It's the same idea. It's the same idea. Again, this is the function of cosine x, and we're trying to find the derivatives at these points, at the highest or the lowest points. The same way we have done for the sine x, right? For the cosine x, we're doing the same thing. We are going to the highest and lowest points and drawing the tangent line. Again, it's parallel. It's parallel to the x-axis. And if we see, these points are actually x equals 0, x equals pi, x equals 2 pi, so on and so forth. And if we start uh, imagining what's going on, okay, we'll see if we draw a graph for the negative sin x. So, okay, what could the graph of negative sin x look like? Again, it's a really basic approach. If we know that the sine curve goes like this, the negative sine curve will actually start in the reversed order like this. Okay, I think you have seen this in the pre-calc course that if we just have a negative sign here for the trigonometric functions, it actually starts in the reversed order, right? Like this in the reversed order. If you know how does the graph of sine x look like, then you'll be easily able to draw the graph of negative sine x. And again, if we draw that, we'll be able to see that at pi and at 2 pi, we have a 0 for this negative sine x function. So these are actually the zeros of negative sine x. Okay. So for the same reason, uh, the graphical approach tells us that the derivative of cosine x should be negative sine x. Now, all we need now is this theorem. This is actually what you will need for the rest of your life. Whenever you'll be doing derivatives of trigonometric functions, you'll be somehow using this. There will be more advanced, definitely more advanced problems, but we'll be definitely using this basic 6 derivatives. So you'll be required to remember these mostly, okay? Especially in this course, if you use these theorems in the problems in the trigonometric functions, you'll see your life will be easier, because straight away, whenever you will see a sine x function, you can just straight away write cosine x for the derivative of it. You don't need to do any hardcore calculation for it. Okay. So what I want you guys is to write these 6, I wouldn't say theorem, I would say formula on a paper and have it in front of you um, for the homework problems. Okay. Obviously, if you memorize this, that still works. But as I said, I don't like the idea of memorizing formulas. Okay, but for the exam, I've asked the course coordinator. He hasn't replied as yet. But if he replies, I'll let you know that if you are allowed to have this formula sheet in front of you in the exam. I hope he allows. Anyway, but we'll be using this formula. Okay. Okay. So let's try one or two problems with this formula. Okay. So what I want you guys to do is to let me share the screen of my iPad. Okay. So now I'm giving you a practice problem, and I'll give you 2 minutes for it, and then I'll solve it. Okay. Let me give you a couple, and you can actually work in groups. I'll be creating a breakout room, and you'll be doing this in a group. Okay. So let me give you a couple of problems for doing it in a group. Let's say the first one is e to the x sin x. Find the derivative of this. Okay. Find the derivatives. Okay. The next one would be x squared tangent of x. And the third one would be slightly difficult, but I think we'll be doing it with ease. Cosine x times, let's say, cotangent of x. Okay, so I want you guys to do this problem. Okay, yeah. So the derivative of e to the x sine x, you can clearly see we need to use the product rule, right? Because we have two different functions multiplied to each other, right? So you can actually use the product rule. Do you agree? And if we use the product rule, we know the product rule says if you have more than one functions working as a product, the rule says keep one and find the derivative of the other, right? In any order, the order won't be a problem because it's the product rule. In the quotient rule, the order will matter. We'll be keeping a certain order. We'll be doing it in a certain order. But for the product rule, whichever order you do, doesn't matter. If you do this first and then go for this one, it will still give you the same result. Okay. Now let's try and use this. Excuse me. So let's try. Let's keep e to the x. We're just keeping it like this, right? And find the derivative of the next. So what's the derivative of sine x? You already have that.
Cos x. Yeah.
Yeah, it's cosine x. So that's the derivative of g, which is sine x on this occasion. Again, you don't need to show these arrows and this and all this. I'm just showing how am I doing it. Okay, you just need to show the algebraic approach, not the scratch work. Okay. All right. Plus, now we'll be keeping the other function. So let's keep sine x, which is the g function, right? And we want to find the derivative of the other function. I mean, the first function on this equation. What's the derivative of e to the x?
Is e to the x.
Exactly. If you have e to the x, we know, we have seen it, that it's actually e to the x. The derivative is actually e to the x, right? And this is exactly what we have here. So group one did a great job. Any question from this one? Any question? Anyone? From any group? Doesn't matter, it has to be, the question has to be from the first group.
I do have a question.
Yeah,
Could you
sure.
simplify that just to e of x on the outside and then parentheses sine of x plus cosine of x?
Yeah, you can do that,
parentheses?
but it's not necessary. You can definitely
Okay.
factor out e to the x, and it will leave you with cosine x plus sine x.
Okay.
It's not required, yeah. Okay. All right, any other question from the first one? Otherwise, you can move to the next one. Okay, let's try the other one. Number two, the derivative of x squared tangent of x. So now, instead of using these arrow signs, I'll be using the same colors, I would say, which I have used here, okay? So that it makes sense to you. Because if I add more arrows, this might look clumsy. So instead, I'll be using these same colors for the same work, okay? So that you can match what's going on and you can match it with the formula. Okay, first of all, again, we'll be keeping the first function. Let's keep x squared. What's the derivative of tangent of x? Anyone? Just see it from the slides.
Secant squared.
Sine square x.
What? Sorry?
Secant square x.
Secant square x. Okay, yeah. Okay. And if I keep the second function, which is tangent of x, what's the derivative of the first function, which is x squared?
2x.
Very good. Using the power rule, right? The power rule says the derivative of x squared is 2x. Because you know, let me write the power rule for you. So the derivative of x to the n is nx to the n minus 1, where this n is 2 for our problem. So 2x to the 2 minus 1, which is 2x, right? Okay, so again, it's exactly the same as the group 2 did. So bravo to them. They did a great job. And the group 3, you don't need to get demoralized. You actually got the toughest problem. So yeah, it was the toughest problem. So even if you couldn't do it, don't get demoralized. We'll be trying to um, solve this type of problems a couple of more times before we appear for the exam. Okay, so no worries, we still have plenty of time. Let's try number 3. Oh, any question from number 2? Any question? No questions at all? We can actually factorize this as well. If we factor out 1x, it becomes x equal secant square x and 2 tangent of x. Again, it's not required, but just in case you need it, I'm just showing how to simplify it. Okay, not really simplify. It's one of those factorized way. Okay, factorized expression. Okay, let's try number 3. Number 3 is cosine x cotangent of x. Excuse me. Okay. Again, we'll be doing the same thing. So first of all, let's keep the first function. Let's keep cosine x. What's the derivative of cotangent of x? Someone from the third group, please. Someone from the third group. Can you tell me, excuse me, can you tell me what's the derivative of cotangent of x? You don't need to memorize it though, at least now. You can see it from the slide. No one from the third group? Okay. So let me do it on behalf of you. It's negative, oops, sorry, I should use the other color. It's negative cosecant squared x. Okay. It's the derivative of cotangent x is cosecant squared x. Negative cosecant squared x. Okay. All right. And if we keep the cotangent x, what's the derivative of cosine x?
Sine x.
No, derivative of cosine x is not sine x.
Negative sine x.
Negative sine x. Very good.
Sorry, negative sine.
No problem. No problem. Okay. So we are done with the formula. Now we just need to see if we can simplify it, or if we can rewrite it, which looks better. So this is basically negative cosine x times cosecant squared x, and then negative cotangent of x times sine x. This is your answer. Okay. I guess you got this part right. Looks like cotangent and oh no. That's wrong anyway. No problem. So this is just the beginning. So Hopefully it will make more sense if you try a couple of more problems. Any question from this third one?
So we had, like, our group had the right answer, but we didn't simplify it. Would we have gotten it right? Like, we didn't rewrite it.
Did you get this one?
Yeah.
But I think I
We were group 2, but we did all 3 of them. Just for practice.
Oh, okay, from group 3. Okay. Yeah. Sorry, I thought you were from group 3. Yeah. So if you don't simplify it, it still should be fine. Yeah.
Okay. Thank you.
But yeah, one thing I would say, if you have something negative, then at least use this parenthesis. Because if you don't use this, let me show you what will happen. This might look like this, cosine x. If you just don't use the parenthesis, it will look like this, right? So this actually looks like you're subtracting cosecant squared from the cosine x, right? At least have this product sign, but often it's difficult to see the product sign. So I would suggest having parentheses instead, okay?
Yes, sir.
All right, so any other question from number 3? Any question you have from any of the 3 problems or from anything related to this product rule or that we actually did a good job. If you can see, we have used the product rule for these 3 problems. We have found the derivative of the exponential function, the trigonometric function, the power function. We have done it all, right? And we have done it in a group, which I always recommend. You should form a group of at least 3 or 4 people to study for the homework or even for the exam, okay? Anyway, so if we don't have any other question, we can take a break for 5 minutes and then we'll come back, I guess, at 10:13, okay? So see you in 5 minutes.